Share screen for these. Okay. You got 30 seconds to get your answers in. All right, I'll be locking answers here in 10 seconds. This has been up since like 12:40. All right, locking answers in 5, 4, 3, 2, and 1. Someone got it in the last second. All right. What was that? Yeah. To get myself in here. So what's the norm of the derivative of that parameterization? Square root of 5 seems right. Why is my iPad not wanting to join? There we go. So to do so, because there's a couple of people who did not get square root of 5. I first need to figure out what is the derivative of this parameterization with respect to t. So what is the derivative of t with respect to t? 1. What is the derivative of sine of 2t with respect to t? Yeah. I think I heard Nabari say it first, or maybe Nakai. And what is the derivative of cosine of 2t? So that when I look at the norm of this vector, take the square root of the sum of the squares of each component. So this would be 1 squared plus 2 cosine of 2t squared plus -2 sine of 2t squared. Which means this is a square root of 1 plus 4 cosine of 2t quantity squared plus 4 sine squared of 2t. I have that common factor in 4, and I see a cosine squared plus a sine squared. The angles inside those are the same, so cosine squared plus sine squared always gives me 1. So then I'll have a 1 plus a 4, which gives me a 5, and the answer is square root of 5. What questions do you got for me? Or Kyle, I did see your email on behalf of Tamia. All right. Yep. Everything, including the stuff that we covered today. It's going to be on that exam on Friday. 4 pages that I want. All right. So today we're going to define 2 operators on vector fields that you'll see a lot, especially in the physics area. So first up is something called divergence. So if you're considering a vector field in 3 dimensions with components P, Q, and R, this is a vector field. And the divergence of F is the following. So one of the ways you're going to see it written is div for divergence. And then just your vector field F. And all the divergence operator is doing is saying, hey, we're going to be summing up the partials in each dimension for each component. So the partial with respect to X of the X dimension plus the partial with respect to Y in the Y dimension plus the partial with respect to Z in the Z dimension. Pretty much, how much are you moving with respect to X in the X direction, adding it to how much you're moving in the Y direction with respect to Y and how much you're moving with respect to Z. Now, this divergence operator can also be written a different way. Kind of hijacking some notation. It can also be written as gradient, as a dot product with your vector field. This is going to be the same thing as just seeing divergence div of F. Where when we saw gradients before, all we were doing was taking the partial with respect to each dimension. So partial with respect to X, partial with respect to Y, and partial with respect to Z. If we were working in just 2 dimensions, and we had a vector field F, well, the divergence of that vector field F is just the same idea of the sum of all of its partials. But how many partials will I need to calculate if I'm working in 2 dimensions? Yeah, just 2. And I add them together. If I was working in 4 dimensions, my divergence would be the sum of how many partials? 4. Because divergence is trying to get a sum total of all the changes in each direction. So when it comes to vector fields, the question is, okay, this is a calculation I can do, but what is it actually trying to describe for me? Well, divergence is just an operator that's telling us how the vector field is behaving towards or away from any point. So you can think of this as a way of measuring kind of acceleration over a vector field. So for example, real quick example. If we had this vector field 2x, 2y, when we first studied this, we were looking at it and we said, okay, well, this is always going to be creating vectors that are pointing away from the origin. All vectors of length 2. Let me do a different color. So for example, kind of if I plugged in 1, 1 into this point, the vector would end up being a 2. So I'd be traveling 2 in the x direction, 2 in the y direction. But then if I move a little bit farther out, so I go to the point 2, 2, what is this vector going to be at that point? X is 2 and y is 2. 4, 4, which is twice as long. My vector is going to be pulling me away twice as fast. If I do 3, 3, I'm going to get a vector and it's going to be pointing away. Where is this vector pointing? So it'd be 6, 6, so 6 in the x direction and 6 in the positive y direction. And it keeps getting, those vectors keep getting longer and longer the farther I go out. It doesn't matter whether I'm looking in quadrant 1, quadrant 2, quadrant 3, and so on. My vectors are always pointing away and they get longer, farther. Or sorry, they get longer the farther away from the origin that I get. What is the divergence of this vector field F? Well, I take the partial with respect to x of the x component. So I take the partial with respect to x of 2x. I'm going to add it with the partial with respect to y of the y component, which is 2y, which is what and what? So I get a divergence of 4 because I'm seeing points changing, right? As I move, I'm essentially going out more than I'm coming in. I'm accelerating as I go out. So this is what divergence is trying to describe. If I had a divergence of 0, that means all the vectors, the energy that's coming into a point and out of a point is the same. I'm not accelerating. I'm not getting faster as I travel in a particular direction. This actually has many applications. One of which is in magnetic fields. So a magnetic field is just a vector field that models the influence of electric currents in magnetic materials. Oops, someone forgot to silence their phone. So magnetic fields are just vector fields. Anyone familiar with Gauss's law when it comes to magnetic fields? What does it state? That's a statement of it.
electric field
over a constant, which means if this is a magnetic field, oops, the I goes before the B. Actually, usually the way you'll see it done in physics text, if you see Gauss's law or Gauss's law depicted in this way, is that the divergence of that field is zero. So if it is a magnetic field, if it is describing a magnetic field, the divergence is going to be zero. So then just really quickly, again, to give us another example of calculating divergence, because it's a relatively simple calculation because it just depends on calculating your partials, what you've done since almost day one of this class, and just making sure you just add up all the partials together. Why did that stop? So then the question I have for you is it possible for the vector field x squared y and then y minus xy squared to be a magnetic field? And just for all those in modern physics, yeah, this is definitely a simplified version of Gauss's law. Just to make a point that this operator does show up. So can this be a magnetic field? Well, what do I need to calculate? Why did it kick me again? What do I need to calculate? The partials make it up, but I'm really calculating what? The divergence of this vector field. If this is a magnetic field, then the divergence should be what? Zero. We expect it to be zero, right? It's not guaranteed if the divergence is zero, it is a magnetic field, but if it's non-zero, I'm guaranteed that this vector field is not a magnetic field. So calculate the divergence. So I take the partial with respect to x of the first component, which is x squared y, and I make sure I add it to the partial of the second component with respect to y, which is y minus x times y squared. So with that in mind, what is, or sorry, with all this written out, what is the partial with respect to x of x squared times y? 2xy. And then what is the partial with respect to y of y minus x times y squared? Which means the divergence of this vector field is what? It'll be 1. The two xy's would cancel each other out, leaving me with just a 1. So can this vector field be a magnetic field? No. Any questions about divergence? essentially, when it comes to this divergence here with magnetic fields, your energy is conserved, right? Total energy in the system is constant. You don't need to be accelerating or decelerating from any point. If you're moving at the same rate. All right, next up is the curl operator, which is a little bit harder to remember. And when I say remember, I mean remember the definition. So if you're considering a vector field in 3 dimensions, we're going to calculate the curl of it. You're always just going to see a written curl, C-U-R-L, of the vector field F. Instead of it being a scalar-like divergence, where it's coming out to be a function or just a single real number, the curl itself turns into another vector field. The x component of this vector field is the difference of your z component with partial with respect to y minus the q component's partial with respect to z. Your y component of this new vector field, the curl, is going to just be your x component's partial with respect to z. So how your x component's changing with respect to variable z minus how your z component's changing with respect to the variable x. And then taking this similar kind of idea of, okay, well, the z component is going to contain partials of the not two z components, p and q. And when I combine those two partials, when I take partials of both of those, well, q is the y dimension. I'm going to take it with respect to the other dimension that I'm considering, x. So the partial with respect to x of q minus the partial with respect to y of p. So this is what the curl looks like in R3. It doesn't have an easy transition into 2 dimensions. In fact, even if you're working within 2 dimensions, your curl is going to end up becoming a vector in 3 dimensions. Oops, sorry, I wrote in R2. Oops. Your curl just becomes a vector field in 3 dimensions where in your x and y component, it's always going to be 0, but you get that same third component. The partial with respect to x of your y component minus the partial with respect to y of your x component. Now, important question is, what is this actually measuring? So divergence was measuring energy flow in and out of any point. What do you think this curl operator is doing? So look at the x component. R sub y is representing what? What was that? Partial of r with respect to y, and partials, derivatives are telling us how something is changing. So how the z component is changing with respect to what variable? Y. Right? Q is the component of the y dimension. So figuring out, okay, what is the difference between how my z component is changing with respect to y and how my y component is changing with respect to z? I'm taking in difference of it. And I do that thing over and over and over again for, or that similar idea for the other two dimensions. And what this ends up doing is talking about rotation. Because I'm talking about these interaction between all different combinations, my X, Y, and Z axis, how I'm changing with respect to the X and Y plane, how I'm changing with respect to the Y and Z plane, and how I'm changing with respect to the X and Z plane. And figuring out also what direction is that rotation going. So curl is going to measure the extent of rotation in this vector field. Of the vector field. And it's at any point in said vector field. Let me write this down. And I'll say it. That is the curl of F at a point P. Is a vector that measures. Well, I said I'd wait. Let me just wait. So the way I like to think of this is if I'm standing right here, I have water flowing on both of my hands. The water on my left half of the body is flowing towards you. The water on my right half of the body is flowing away from you. If I use my arms as paddles, what is going to happen to me is that water starts flowing. Left half is going to want to go forward. Right half is wanting to go back. And then effectively, what is happening to my body? I spin, and I'm going to hit this point right here. And if I can't find an equilibrium essentially with energy, I'm going to get here. I'm just going to keep floating back and forth until I do so. Any object that is positioned like this will end up spinning. Okay, curl is measuring that type of spin from just the vectors that you're experiencing. That's why it's still in two dimensions, right? You're only thinking forward and back. I still have rotation, which is why curl in two dimensions still produces a vector field. My rotation is on a different axis. It's not on the XY axis. So what time is it? 1:31. Cool. So I got time for two examples. One's going to be more interesting than the other because I want us to do this calculation, because one of the best ways to try to start remembering how to calculate curl is just by doing it. Okay. You technically get a little bit more exercise with in the homework. So I'm just going to give us some vector field right here. So the first x component is sine of x times cosine of z. That's what's going to determine the length of all the x components of any vector, e to the y plus x times z for the y component, and x times y times z for the z component. So the way I like to break these down is first recognize what are the three components, the p, the q, and the r. Well, my p component was just that sine of x times cosine of z. John, what's my q component? Hoping that adrenaline rush will help you stay awake. It's all good. We're all tired at the end of the semester. Anyone want to help him out? Yeah, you're getting there. E to the y plus xz. Well, our component is just x, y, z. And if I just keep this in mind, the component p, I only need to calculate its partial with respect to the other two dimensions, with respect to z and with respect to y. My y component, q, I only need to calculate the partials with respect to z and with respect to x, the other dimensions. And then same thing with r, my z dimension. I only need to calculate its partials with respect to x and y. So since it's the x dimension for p, I need to find the partial with respect to y and partial with respect to z. Well, what's the partial with respect to y going to be for sine of x times cosine of z? 0. X and z are considered what when I take the partial with respect to y? Constant. Derivative of any constant is 0. What about the derivative, the partial with respect to z? What is it going to be? So sine of x is a constant, right? Which really means I just take sine of x multiplied by the derivative of cosine of z. And the derivative of cosine of z is negative sine of z, which sounds like multiple people are essentially getting there if you didn't actually get there. Those are the two partials I'm going to need for my x component. For my y component, q, what two partials am I going to have to calculate? X and z. So what is the partial with respect to x of e to the y plus x times z? It won't be x, it'll be z, but z e to the xz. Derivative of any exponential function is just the derivative of the numerator times the same exponential function. Take the derivative of the numerator with respect to x, it's just going to be that constant coefficient of z. What about qz? So the partial of the q component with respect to z. All right, and now for the z components, I need to calculate what two partials? X and y. So what is the partial with respect to x of x times y times z? Y is z. Then if I take it with respect to y, it's going to be xz. So then now that I have all of those partials, I just need to make sure how I combine them. So the x component is going to be, well, I take the partial of the z component with respect to y, ry, and subtract it from the partial of the y component with respect to z. Ry minus qz. This is just x times z minus x times e to the y plus xz. Now look for the y component of my curl. I might not remember the partials, but I know the y component is going to be combining the partials of what two dimensions? The z and x, the other two. So I know I take the z, or sorry, this one I take the p, the x first. And I subtract the y component. And then the question is, what are the partials? Well, it's for the opposite, what I'm subtracting it with. So what is that, LeJohn? For p, it'll be what partial? No, you never take the partial with respect to the same dimension. So it'll be z, and then for the r, it'd be the partial with respect to what? X. Which means, whoops, I wrote that too low. This is just going to be negative sine of x, sine of z. Minus yz. And then the last component is the z component, which means I'm going to be taking the difference of the y and x component. So since I'm comparing y and x, the y component q, what partial do I use here with respect to x? For the p component or the x component, I take the partial with respect to y. So this is z times e to the y plus xz minus py, which was 0. And there is my curl in my vector field. At any given point, x, y, z, I can tell you what the rotation is at that point. So just any questions about the process? Okay. Get you back into another physics example. Call that the force from gravity can be defined by the following vector field. You have a gravitational constant. Multiply the two masses together. And then the pull in the x direction is determined by your position in the x direction. And then your distance from the center of the larger mass, which is going to be squared plus y squared plus z squared to the 3/2. It's technically not distance because if you remember, it's what, negative g m1 m2 over, was it r, and then you have in here x over square root of r, y over square root of r, z over square root of r, which is where that 3/2 is coming from. But it's similar for the y dimension and z dimension. X squared plus y squared plus z squared to the 3/2 and z of x squared plus y squared plus z squared to the 3/2. What we're going to do is show that gravitational field has no spin. Essentially, if I get caught in gravitational field of an object and I start getting pulled towards it, and I'm equal distance, essentially, again, that idea of the stream, I'm standing like this, the left half of my body and right half of my body are going to be pulled towards the center of that object at the same rate. I'm not going to be rotating in place. So if I want to show that there's going to be no spin to this vector field, I'm going to calculate the what of the vector field? Yeah, the curl. So I need to find, okay, well, what is my x component? What is my y component? And what is my z component for this vector field? And then take the partials with respect to the other dimensions. Well, the x component is just it's right here, x divided by the square root of your the square root cubed of your distance. So x over x squared plus y squared plus z squared to 3/2. My y component, x squared plus y squared plus z squared to the 3/2 of my z component, z over x squared plus y squared plus z squared to the 3/2. So I need to take, for this x component p, the partial with respect to y. When I look at that component, where do I see a y term? Do I see it in the numerator at all? No, which means when I'm taking the partial with respect to y, this x in the numerator is just a what? Constant. So I'm going to rewrite this as x times x squared plus y squared plus z squared to the negative 3/2. Because then this is a constant multiple I can essentially pull out front, multiply by later. I just need to figure out what is the derivative of this thing right here. But again, x squared and z squared are going to be constant because I'm taking the partial with respect to y, which means I use chain rule here, but the outer part's just power rule. Bring the exponent down, leave what's inside, subtract 1 from the exponent. But then chain rule says I need to make sure I multiply by what? The derivative of the inside. So derivative of x squared plus y squared plus z squared, which is just going to be what? 2y. Just 2y. So this is going to become an x times a negative 3/2 times x squared plus y squared plus z squared. If I take negative 3/2 and subtract 1, what do I get? Negative 3/2 minus 1. Negative 5/2. Subtracting 1. And then I multiply by the derivative of the inside. Which, if I combine all these together, well, I have an x times a negative 3 divided by a 2 times all of this times a 2 times a y. Well, that's just going to become a negative 3xy times x squared plus y squared plus z squared to the negative 5/2. Does everyone see that partial, how we got it? Because we're going to see now that we've done this once, all the other partials are going to be following the same manner. We're going to be able to say what all the partials are. But if I took the partial with respect to z, well, again, x is considered what? Constant. The only place I have a z is in that denominator. So I would move it up and I'll be looking at, instead of partial with respect to y of this, partial with respect to z, which still means I'd pull that x out front. I'd do chain rule, bring the -3/2 down front, leave what's inside. I'm going to subtract 1 from the exponent, but then multiply by the derivative of the inside with respect to z, which means I won't be multiplying by a 2y, I'd be multiplying by a what? Not 2x. Taking the derivative with respect to z, so a 2z. So the only thing that would change from the partial with respect to y to the partial with respect to z is, instead of having a -3 times x times y, I'm going to have a -3 times x times z. Times x squared plus y squared plus z squared to the -5/2. And then when I go to q, I'm going to have to take the partials with respect to what two variables for my q component? X and z. But hey, look, wait a second. If I take the partial with respect to x, I get the same flavor derivative that I had over here, right? Only where I see an x is in this denominator, where I see z is in this denominator, all right, rewrite that as the exponent. That y is just a constant multiple. I'm going to have, again, chain rule, -3/2 out front, leave what's inside, subtract 1 from the exponent, but then I take the derivative of what's inside with respect to x, and the derivative of x squared plus y squared plus z squared with respect to x is just a 2x. Meaning that this partial is just going to be a -3 times an x times a y times x squared plus y squared plus z squared to the -5/2. What is the partial of q with respect to z going to be? If I go to r, take its partial with respect to x, well, I'm just going to have then a -3 times an x times a z times that same x squared plus y squared plus z squared. All to the -5/2. So that when I calculate the curl of this vector field for gravitational pull, in the very, very first component, just let me write it above again. And take the z component, subtract the y component, but I take the partials. Since I'm comparing z and y, the z component, I consider what partial? Y. And the z component has what partial? Z. So ry qz. Well, ry is at -3yz. And for simplicity, because I see the time, actually, R might be misleading. Someone else give me a variable. What was that? Z? V, sorry. V. So just so I don't have to keep writing that x squared plus y squared plus z squared to the -5/2 so many times, We're just going to let it represent it as V, as in volleyball. So then if I take the partial of R with respect to Y, it's at negative 3YZ times my V. And then I'll be subtracting Q's partial with respect to Z, which was what? Negative 3ZY times that V. Oh, hey, look at what's going to happen there. They cancel each other out. I'm going to get a 0. And I do this for all my other components. So if I'm in the Y component, I'm going to take Z and X. I'm going to compare them. I'm going to take the X component and subtract the Z component, which means I mixed up the partials. But hey, the partial with respect to Z of the component P was negative 3XY times this V, and I'll be subtracting a negative 3XY times that V, which again gives me what? 0. And then I see the time. So this one is right, no, Q. Q minus P, XY, give me negative 3 XY V minus negative 3 XY V. Essentially, if the only force acting on two objects is gravitational force, neither object should end up spinning. Those objects end up spinning is because there's external forces being applied to it. But that's all I got for you today. I'm already much more over than I wanted to be. So if you have any questions for me, let me turn it so we can get more of the work. If you need it, feel free to ask. Otherwise, enjoy a little break before Diffie Q. Stop the recording.